On to section 1.5, normality, quotient groups, and homomorphisms. So again, we're touching on a topic that you were exposed to in senior level algebra. What we'll do is relate several ideas, as the title of the section suggests. You probably spent a bit of time on this in your senior level algebra class. The senior level book I prefer, Fraley, that I mention so often, calls one of the things we're about to encounter factor groups. A more common term is quotient groups. We're going to make a group out of cosets. Cosets of a particular kind of subgroup. That subgroup will be normal, to be defined at great length, in fact. And we'll tie this into the existence of certain kinds of homomorphisms. Now, the Fraley book starts with homomorphisms, then from the kernel of a homomorphism builds up quotient groups. We're going to do it in a little bit different way and use a different terminology. So anyhow, if you happen to have your senior level algebra from Fraley's first course in abstract algebra or something along those lines, we're covering the topic of factor groups from there. We will call these quotient groups. The majority of the world calls these quotient groups. Factor groups is a term I've really only heard from Fraley, and there's reasons to call them factor groups, as we'll see well on down the road. First, a result. Actually, what we're setting up here is, if I can move past theorem 1.5.1, we're defining what it means for a group to be a normal subgroup. So first, the definition is a subgroup N of a group G which satisfies any of these conditions we're about to state, and we'll show in the theorem that those conditions are equivalent, is called a normal subgroup of G. The notation is to use a little triangle there for normal subgroup versus just the usual less than sign for subgroup. And theorem 1.5.1 says, if N is a subgroup of group G, then the following conditions are equivalent. And if subgroup N satisfies any of these equivalent conditions, then it's called a normal subgroup. First, left and right congruence modulo N coincide. They define the same equivalence relation on group G. That's equivalent to every left coset of N in G is a right coset of N in G. In turn, equivalent to left coset AN equals right coset NA for all A in group G. Fourthly, for all A in G, the set A in A inverse is a subgroup, is a subset of subgroup N, where by A capital N A inverse, we mean the obvious kind of thing. That's the set of all elements of the form A in A inverse, where we let that little center N value range across all of set N, or all of subgroup capital N. And fifthly, for all A in G, A capital N A inverse equals capital N. So we'll go through and establish that all five of these are equivalent. So we'll take advantage of the transitivity of implication, and we won't have to show all five choose two things. But quite a bit of stuff to do to show these five things are equivalent. Good news, it's mostly computational. Okay, and we'll elaborate on the meaning of those things as we go. All right, so theorem 1.5.1. Here we go. Let's show 1 implies 2. So we're going to show if left and right congruence coincide, modulo N. Then, secondly, every left coset of N in G is a right coset of N in G. Okay. If left and right congruence mod N coincide, then we've got A is left congruent to B, AB inverse, I think this is right congruent. AB inverse is an element of N. A is right congruent to B, if and only if A inverse B is an element of N. A is left congruent to B. So this is simply taking the definitions of left and right congruence, if I've kept them straight, which is which, But we're saying one of these occurs if and only if the other occurs. We've got left congruence if and only if we have right congruence. And we want to show every left coset of n and g is a right coset of n and g. So I don't have to show anything as specific as part 3, but here we have a left coset equal to a very specific right coset. Here we've got the same element of a on both sides of this equality. We're actually going to establish that. That's not something as specific as we need to establish, but we'll discuss these two again shortly. But we're trying to show that every left coset of n is a right coset. So consider the left coset A capital N. Let X be an element of that coset. Then being in the left coset means A inverse X is an element of N. And having that hold, we must also have AX inverse an element of N. That's the left and the right congruence situation there. Saying X is in a coset is saying it's in the left congruence class containing A. So that's where the left congruence comes from. And the assumption that that's equivalent to right congruence produces this, written simply in terms of elements of subgroup capital N as opposed to the little congruence notation. So let's see, we left off with AX inverse is an N. All right, N's a subgroup, so AX inverse inverse, that is X A inverse, finding the inverse of a product here, that must also be an N. If XA inverse is an N, then if you like, X is right congruent to A, that is X is an element of coset N, capital N A, is given here. If you don't like that, then what we got here is XA inverse equals some element, say N, of this subgroup capital N, and then we multiply on the right by element A, and we get X to be of the form N times A. X is of the form N times A, where N is an element of subgroup capital N. So we can look at this as set manipulations. Probably we're going to want to start doing that to speed things along a little bit. So we can look at it in terms of set inclusion or in terms of right congruence. So we've shown that an arbitrary element of the left coset A capital N is also an element of the right coset capital N A. So we've shown A capital N is a subset of N capital N A. So this left coset is a subset of that right coset. We can go through similarly and interchange the role of AN with NA and get the subset inclusion reversed very similarly. Normally I put all the details in, but that's just a slight rearrangement of the manipulations. And we'll draw the conclusion that AN equals NA, showing that this left coset is also a right coset. In fact, a particular right coset. So we've established part 2. We've actually established part 3. Part 3 is a special case of part 2. But we've established part 2, and that's the implication we need when we link all these things together to show all 5 of these things are equivalent. Okay, next we want to show part 3 implies part 1. Part 3 says coset, left coset AN equals right coset NA. This holding for all A in group G, the big group in which all the action occurs, implies left and right congruence modulo N coincide. So suppose left and right cosets are equal, and let A be right congruent to B. Excuse me, I said all this stuff was computational. So here we go dealing with elements. So we'll take the right congruence, A is right congruent to B, rewrite it as AB inverse is an element of N. The congruence was mod N. if AB inverse is in N, and the inverse of AB inverse, that is BA inverse, is in N, and BA inverse being in N is equivalent to B being in NA, we can deal with it in terms of the fact that these right cosets are equivalence classes in terms of right congruence, and that's what we've got here is right congruence. Or you can think, I know BA inverse is an N. If I multiply on the right by A, we'll get B. Multiply on the right by A, we'll get the set that consists of capital N times lowercase a. So I could sort of think of it almost as a cross multiplication. It's a legitimate manipulation, and we've got two approaches to this. But anyhow, we do get the inclusion that B is in capital NA. Now we've supposed these left and right cosets are the same, so B is also in A capital N. Now, with B being in A capital N, we could similarly multiply both sides of this on the left by A inverse and get A inverse B as an element of N itself. I can also write it in terms of elements and get a little less directly to this. But this relationship specifically means A is left congruent to B, mod N. And we've shown that if A is right congruent to B, then A is left congruent to B. We need to interchange the roles of left and right congruence. It's another similarly thing. Assume A is left congruent to B mod N, and similarly, you can derive that A is right congruent to B. So if left cosets equal right cosets is given here, then left and right congruence coincide. What it amounts to when we're done with this is we're going to define any one of these properties to be the property of a normal subgroup. So we immediately know a bunch of stuff about normal subgroups. We'll know 5 things about normal subgroups, these 5 properties that we're establishing. Okay, part 2 implies part 3. Every left coset of N and G is a right coset of N and G, implies AN equals NA, as given here for all A and G. Okay, let's just chat about this a little bit. Saying every left coset is some right coset is not saying this. Well, granted, this is a left coset and this is a right coset, but what we're given in part 2 is say that the left coset AN equals some right coset. Maybe I don't use the same representative over here, but there is some representative over here such that this left coset equals some right coset. Okay, so let AN be a left coset of N and G. Then we've hypothesized part 2. We've hypothesized that that left coset is a right coset. Okay, so AN equals NB for some B. Like I said, I can't necessarily put the A there. I simply know this left coset equals some right coset. Okay, so we get a right coset, and right cosets are of this form. The identity is in N because it's a subgroup. So if we look at A times the identity, of course that's just A, we get something that's in AN. I've taken an element of N, the identity, and of course that produces A. A is a representative of the coset AN. The A there is always in that coset. And we've hypothesized that this coset equals a coset NB. So we've got A in AN. Similarly, take the identity in N over here, and we get A as in NA. Yeah, duh, of course. A is a representative of a coset. So A is always in the left coset. What was I thinking? It's always in the right coset as well. So we've got A in the right coset in B. We've also got A in the right coset in A. So it's in the intersection of those 2 right cosets. I had to anchor it as right cosets. But remember, the right cosets say of N partition G. That means either they're disjoint or they're the same. Well, these two ain't disjoint. We found a thing that's in both this right coset and that right coset. Well, that only happens when those cosets are equal. So we can draw the conclusion that AN equals NB and NB equals NA. So we get the conclusion AN equals NA. We started with an arbitrary left coset of N, so we effectively started with an arbitrary element of G. So that's the for all A and G part that establishes part 3. Okay, part 3 implies part 4. Part 3, left and right cosets coincide. Quite often that's something that'll be useful in manipulations, though we will know all 5 of these things. But left and right cosets are equal as given, implies part 4 for all A and G, A in A inverse is a subset of N. I think we mentioned this earlier, where by A in A inverse, I mean the obvious set. The bulk of these things we're talking about here are sets. N is a subgroup. The cosets, not necessarily subgroups. This thing here, not necessarily a subgroup. So assume 3, assume left and right cosets are the same. I'd be awfully tempting to say, well, let's just multiply on the right-hand side by A inverse. We'll pick an A inverse up over here, and we'll lose this A on this side. And there's some validity to that. In fact, we're establishing something like that in part 5. But these are easy to remember properties because they behave in pretty predictable ways. But let's look at this element-wise. So let N be any element of subgroup capital N. Then AN is an element of NA. We've assumed equality of left and right cosets as hypotheses. A lowercase n is certainly in A capital N, and that's the same as this set. So we get AN to be in this right coset. So if you like, I could multiply both sides by A inverse, dealing with an element over here, and then I would get an element of just N itself. I could choose an N prime over here and manipulate elements to establish this if you like. We've said an element of, so I get a subset inclusion if I put this argument together. Geez, I kind of like this. I like this one. This asks us to show something is a subset of something else. And I think all the other stuff asks us to show like equality, coinciding. Maybe my favorite of that list of things in Theorem 1.5.1 is this showing of a subset. That seems like less work than the claims of the others. I guess effectively it isn't because they're all 5 equivalent. But there's a quick little proof on that one. Next, part 4 implies part 5. So suppose we get the subset inclusion. We want to show that actually implies set equality. Okay. Suppose the subset inclusion. This is holding for all A and G. So take A, replace it with A inverse. So we're going to A inverse here and A inverse here. And that gives us A inverse NA as a subset of capital N. So for any element, lowercase n, in the subgroup, then we have N equals, well, it equals the identity N times the identity. So the identity is A inverse here and A inverse here. You can't argue with the validity of that because we just multiplied on the left and the right by the identity in a certain form. We can associate the A inverse with the N, and the A with the N is given here. So associativity gives us this kind of property. Hey, but A inverse lowercase n A, that's an element of the set A inverse set capital N A. So this in parentheses is an element of this. All right. So here we've taken an element of this, something in N. We've multiplied by A inverse for the thing in parentheses on the left and the right. So we're getting something in A capital N, A inverse. In parentheses, that's a thing in capital N. So when I multiply that thing on the left by element A and on the right by element A inverse, I get a thing that's in A capital N, A inverse, because the thing in parentheses is itself an element of capital N. It's kind of the downside of a computational proof. But we get that inclusion. And so we've shown if I take an arbitrary element of capital N, then that thing is also in A capital N, A inverse computationally. So set capital N is a subset of this A capital N, A inverse stuff. We had hypothesized, assuming for that A capital N, A inverse is a subset of N. We've reversed the set inclusion here. So we draw a conclusion of equality of the two sets. So if we have this subset inclusion, then we have actual equality of sets. That's what we've established. And I think this wraps up the logic. If you'll go through and see the implications we've done, you'll see this will establish all of the implications. 5 implies 2, so we're going to show equality of these two sets implies 2 left cosets and right cosets. Every left coset is a right coset. So left and right cosets coincide is what we're attempting to show. Well, if A capital N, A inverse equals N, that's our hypothesis. That's what part 5 states. Then AN equals NA. Think of it as multiplying on the right by element A. Again, we could chase this with elements of N on this side and a different element of N on that side and show some element-wise subset of this, subset of that, and draw the set inclusion. But like I said, let's speed that up a little bit. This is a legitimate manipulation of these sets to get left coset equals right coset. This held for all A and G, so every left coset is a right coset. In fact, it's a specific right coset, which wasn't required to show part 2, but showing that it's a specific one does show part 2. Actually shows part 3 as well. So there's, back to the notes, 5 things. Any of those 5 things being satisfied by subgroup capital N of group G, capital N is called a normal subgroup. Why you would want to look at this, it's not clear at this stage. You know, if you've done this before, and you should have in your senior level algebra. Yeah, with normal subgroups, I can take quotient groups or factor groups in the verbiage of Fraley. And that's what we need to establish now. Maybe emphasizing normal subgroups, I use this little triangle notation. N is a normal subgroup of G is the way to read that. What's up with normal subgroups? Well, if we had an abelian group, every subgroup of an abelian group is a normal subgroup. So if we had commutativity, then pick your favorite, maybe this one. If we had commutativity, of course, this set of elements equals that set of elements if we have commutativity. We're not really here to use the normal stuff so much on commutative groups, abelian groups. But if we had commutativity, certainly we'd have a normal subgroup by part 3 of theorem 1.5.1, say. So what if we had a non-commutative group? That doesn't mean you don't have normal subgroups. This would be a pretty brief story, which would be a rehashing of commutative and non-commutative groups. But if we take any subgroup, capital N, of index 2 in a normal, in a group G, that subgroup is a normal subgroup. Any subgroup of index 2 is a normal subgroup. Exercise 1.5.1, that's to be shown. Quick review. What do you mean by index 2? That means group G has 2 cosets of N in G, N itself, and another coset. And those 2 cosets together partition group G. So N has half the number of elements that G has. Yeah, well, it's fine if it's finite, but suspect if G is an infinite group, the funny behavior of infinities. But anyhow, yeah, there's two cosets. In a crude sense, half the elements of G are in itself, and the other half are in that other coset of N in G. And we can go through and confirm that having only two cosets, that's the thing that matters. You can confirm one of these things, showing that that N is actually a normal subgroup. Like I said, I'm kind of drawn to this one usually. If there's only two cosets and they partition G, there's not a lot of place elements can be. They're either in N or they're in the complement of N, the other coset. So this right here would give us an opportunity to find normal subgroups of non-abelian groups. The intersection of any collection of normal subgroups of G is itself a normal subgroup. You're asked to show that in exercise 1.5.2. You know, intersections of subgroups or subgroups. The claim here is the normality claim. The intersection of normal subgroups, or again, normal subgroups. Okay, let's talk about normality a little bit here. The definition, I'd like to say, is fairly straightforward. Yeah, I think it takes some getting used to, though. Here's some maybe surprising observations. It may be the case that for group G, we have subgroups of G satisfying N is a normal subgroup of M, and M is a normal subgroup of G. So we got this string, N is a subgroup of M is a subgroup of G. But the normality condition doesn't satisfy like a transitivity like regular old subgroup stuff does. It may be that N, being a normal subgroup of M, may not be a normal subgroup of G, even though M is a normal subgroup of G. To be shown, probably by example, in exercise 1.5.10. Does that make any sense? Let's go back to the definition. So let's see, N being a normal subgroup of M, what's that mean? Back to the definition. Like I said, I like part 3. It's common to define a normal subgroup as one satisfying this and then establish all this other stuff. Maybe that's why I like this one. But saying we have a subgroup, a normal subgroup of a given group. What was that? N was a subgroup of M, normal subgroup of M. Yeah, N's a normal subgroup of M. Means left and right cosets of N in M coincide. So if I take any element of group M, any element A in group M, we get this kind of behavior. That's what it means for N to be a normal subgroup in group M. And remember, we're trying to jump to the conclusion, well, we can't apparently jump to the conclusion that N is a normal subgroup of G. Well, what could go wrong? Well, here's what could go wrong. I've got left cosets equal to right cosets when this element A comes from M, but M's a subgroup of G. So there's more stuff in G than there is in N, and it could be some of the stuff in G doesn't satisfy this left and right coset stuff for N itself. So with an eye towards this part 3 on what normal means, this shouldn't come as a great shock that we don't have this transitivity of normality. Now, something that does work, another observation, is the following. It's kind of the same idea. If N is a normal subgroup of G, and M is a group between N and G, N is a subgroup of M is a subgroup of G, then N is a normal subgroup of M. Does that make any sense? What does it mean for N to be a normal subgroup of G? It means AN equals NA. Left cosets and right cosets are the same with respect to element A for all A in G. What does this mean? This means left cosets of N equal right cosets of N. AN equals NA for all A in the big group here. And the big group here is M. Of course that happens because that held for all A and G, and M contains only some of the A's and G. So this is actually a weaker condition. So certainly, if N is a normal subgroup of G, then N is a normal subgroup of any other groups between N and G in this sense. And that's very straightforward. That comes from my favorite part up there. Left and right cosets coincide, say. This other part, it's not clear. It shouldn't be surprising that this is a problem, but it's not clear that it's necessarily a problem. So this observation here in particular, along with the stuff we have from the previous theorem, will be useful in the proof of the following. So the situation here is let K and N be subgroups of group G within a normal subgroup in G. So we don't have just subgroups. We've got subgroups of G, one of which is a normal subgroup. This is another one of those settings where G is the umbrella group and everything's happening inside group G. Claim 1. N intersect K is a normal subgroup of K. Quick observation, N intersect K, that is a subgroup of K, it's a subset of K. Yeah, that'd be a subgroup. Remember, intersections of subgroups are subgroups, and K and N are subgroups of G. So N intersect K is a subgroup of G. The normality stuff is to be established. Secondly, N is a normal subgroup of, remember this, N join K, the join of these two sets. This was, apparently, first off, must be a group because they've used the normal subgroup symbol there, so the highlighted thing must be a group. We'll recall this in the proof. It's the group generated by the set in union K. So it's the subgroup of G generated by all the elements in N and K together in union K. So it is, in fact, a group. And it certainly contains N. So this is a reasonable thing to claim. What needs to be established is the normality stuff. Part 3, and arguably this may be the most useful, says NK equals N join K equals KN. Okay, we define NK in this setting as a set, not a group. We said if K and N are subgroups or subsets of group G, then this denotes all elements of G of the form little n times little k, an element of this set times an element of that set, in that order. So even when N and K are subgroups, this may not be a subgroup, but we're getting some information about that right here. The claim is this set equals N join K equals that set. Okay, we're not making a claim of commutativity, though it looks like something commutes, not necessarily everything commutes. Also, hey, this is a group. It was a group generated by the elements in union K. That's a group. Well, if that's a group, then these two things are groups because they equal that. Yeah? So we took K and N as subgroups, and we did get NK and KN to be a group itself. Why didn't this work before? Because we got this new hypothesis now. We've got N as a normal subgroup in G, and it's the normality of N that's giving us the fact that that stuff is not just a set, it's actually a group. And fourthly, if K is a normal subgroup of G, so that'll give us a situation where both of these are normal subgroups of G, and K intersect N is the identity element of G. So these two subgroups are, I don't know, essentially disjoint, might be a kind of term that would be used here. They're almost disjoint. They got to both have the identity to be subgroups, but they're as disjoint as they can be. They have to have the identity in common. But that's the only thing they have in common. Then the claim is NK equals KN for all lowercase k and lowercase n from the obvious place. So we are getting some kind of commutativity here. All right, let's go through the proof of that. Again, fairly computational. So wish I could draw you pictures, but mostly computational. Like I said, let's start with the idea of what it means to have a join of two subgroups, this join symbol. The join of subgroups, say H and K, we use some different symbols here. I'm saving N as kind of a special symbol. It denotes that normal subgroup. But in general, the join of subgroups H and K of a big group G was a group generated by H union K. So you know that join is a group. It's a group by definition. We took this set of elements and saw what group does this generate. That's the join of groups, subgroups H and K, say. Okay, first off, so we're not showing equivalence, we're just making flat out 4 claims. First claim, N intersect K is a normal subgroup of subgroup K itself. Okay, we got some options here. Looks like we're going to use theorem 1.5.1 part 4, which dealt with something of this form in terms of a property of normal subgroup. So we show something of this form, and we've got it. Like I said, we'll use that theorem 1 from this section extensively, and it's got a bunch of parts, so we got options. So we'll take N to be an element of N intersect K. So we're taking an element of this group on the left, and we're taking A to be an arbitrary element of K, right? We want to talk about, ultimately, I guess, about cosets of this in K. So we need to choose an element of K. Choosing A as the symbol. I don't know if I got that idea from Hungerford or if I made this up. Yeah, we wrote theorem 1.5 with a lot of use of the symbol A from the big group. Here the big group is K in this little claim. All right, then element A times N times A inverse. That's an element of subgroup N. Remember, N is a normal subgroup of G. So if we take any element of G, call it A, and I multiply on the left and the right by A and A inverse, that element of N will again be an N. That's because a capital N, A inverse, is a subset of capital N. That's a property of normal subgroups. So we get this kind of behavior from theorem 1.5.1, forget which part, but we get this kind of behavior by the very definition of normal subgroup. And this holds for all elements A and G. Yeah, we're really only interested in A and K, but if A is an element of K, well, K is a subgroup of G, so A is in G as well. So we can conclude this. A in A inverse is in K, since K is a subgroup of G, and we've assumed A is in K, so it's just a closure thing, and we've assumed N is in the intersection, so in particular N is in K. Since N is in K and A is in K, in group K, the product A in A inverse is in K, just closure of that subgroup K, making sure the appropriate letters are in the right place. They're in subgroup K. Such A's satisfying these conditions give us A in A inverse is in K and in N. So we establish both of those. So A in A inverse is in the intersection of N and K. It's both in N and in K. So here we have an element of N intersect K. Let's take that element, put some maybe parentheses around it. If we were to multiply on, going a different direction. Let's look at the form of this. We've taken an arbitrary element of N intersect K, multiplied it on the left by A, the right by A inverse. A is an arbitrary element of K, and we've got something in N intersect K. So for any element lowercase n and capital N intersect K, we get this behavior. What we've shown is the set A N intersect capital K. A inverse is a subset of N intersect K. That's exactly what we had in theorem 1.5.1 part 4, but we didn't have an intersection here. Here we had a group, and here we had a group denoted N. And that was a property having something of the form A capital N, A inverse is a subset of N itself. That meant N was a normal subgroup in wherever the A's came from. So here we don't have N, we have N intersect K, and the A's came from K itself. So this thing is a normal subgroup of that thing. N intersect K is a normal subgroup of K itself. Part 4 of that previous theorem. So then straightforward computations, kind of tedious stuff if you ask me, but that's algebra for you. Next claim, N is a normal subgroup of the join of N and K. Well, N and K are subgroups of G, so the join is also a subgroup of G by the very way the join is defined. N is a normal subgroup of G. That was hypotheses. Since N is a normal subgroup of G, and this includes only elements of G, then N is a normal subgroup of this. That's that observation we made about the N, M, and G before we got into this. It's in the notes. So think left coset of N equals right coset of N for all A in G. And when I make a normality claim about this group, then I use A from here. But all A's in here are also in group G. Group G contains everything. It's an umbrella group. So we get a normality of N in this group as well. This is simply some subgroup of G. Call it M to match what we had earlier in the notes. So we get the normality claim justified there, and that's actually the easiest of these four probably. Thirdly, probably the most useful of these claims, we'll look at products of groups. We'll look at sets of this form in the future. Do these sets in general form subgroups when K and N are subgroups? No. But if you look at a set of this form where K and N are subgroups of a group G, and one of these is normal, then you're getting a subgroup. That's part of the claim here. Okay, so claim of equality on these things. This one's a little more subtle. First, NK is simply all lowercase n times lowercase k. That's the meaning of that set. N join K is the smallest group containing all the elements in N union K, and that's how we defined a group generated by a set of elements in a larger group. So NK, certainly it's a subset of the group generated by N union K. I mean, all of these things are in the group generated by N union K. Yes, in fact, we'll look at what elements in the join look like here shortly, but this certainly are some of the things in the group generated by N union K. Yeah, there'd be KNs in there as well, right? If it's generated by a set, then I don't have a preferred order. I do here when I write these symbols. This set is an element of N times an element of K. This group includes that and includes elements of this set times elements of that set in that order as well. In fact, we know exactly what the elements of the join look like symbolically. But certainly we have NK as a set, as a subset of this group generated by N union K. Now take yourself X, an element of N join K. Theorem 1.2.8 told us what the elements look like in a group generated by a set. What we had was powers of those elements intermixed. We had products of powers of elements. First, if I take an element of N and raise it to a power, I get another element of N because it's a subgroup. If I take an element of k and raise it to a power, I get an element of k. So I don't have to deal with the power stuff here, because here we've got more than a set. We've got n and k as themselves as groups. So what does this element x look like? It's an element of n times an element of k times an element of n times an element of k, blah, 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 element of n times element of k. How do you know it doesn't start with an element of k? Well, fine, make that the identity, and then that'll take care of that. You can drop it. But we get something of this form. X is of this form, where, of course, the n's are from set n, subgroup n, and the k's are from subgroup k. So X is of this form. Well, what are we up to here? We know nk is a subset of the joint. We're taking an element of the joint, and we want to show that's an nk. So I want to see an element of n times an element of k. That ain't what I see. I see a bunch of n's mixed up with a bunch of k's. Yeah, but remember, n is a normal subgroup. That means left cosets and right cosets are the same. They coincide. an equals na symbolically. Since n's a normal subgroup of G, then consider the coset n k sub I times k sub I n. Taking one of these subscripted k's. The k's are from subgroup K, so these k's, they all live in G. We got a normal subgroup of G, so knowing we have a normal subgroup N in G, I know n k sub I equals k sub I n. This right coset equals that left coset. That's part 2 of theorem 1.5.2. The 1.5.1, wasn't it? Equality of left and right cosets. The definition of normal. Okay, so that means if we look at n sub I, k sub I, one of these things here, n sub I, k sub I, well, that's an element of this coset. It's multiplied on the right by k sub I, and on the left, there's an element of subgroup n. But these two things are equal. So that element of this set is also an element of that set, which means it can be written as k sub I times something else in capital N. So we get n sub I, k sub I equals k sub I, n sub I prime. Because left and right cosets are equal, we can say that. That's not commutativity, because I know I've got the same k sub I because of the way we're dealing with the cosets, but I don't know I have the same element of capital N. I know I have an element of capital N. So I'm not getting a legitimate commutativity here. I am allowed to take an element of n times an element of k and write that in a specific form, an element of k times an element of n. And it's the normality of subgroup n that lets us do that. So what are we trying to do? Trying to show this product, this is x, is in nk. I want to write this as an element of n times an element of k. So here's a plan. Let's get all the n's on the left and all the k's on the right. Well, this lets us swap orders in a sense. It changes the n's. So what we're going to do is take this idea and look at, and the indices are different, but that's irrelevant. Look at K1 times N2. That's something of this form. And we could write it as something of this form. So we could take K1 N2 and rewrite this as the product N2 prime times K1. I can move the K to the right. So maybe the primes are in the wrong place. But if I look at that one, I can take the fact that we've got a K sub I times something in N and rewrite it as something else in N times K sub I. I can move that to the left and that to the right. So I can swap the orders on these, but in doing so, I'll change the element of N. I won't change the element of K. Same K on both sides. So what we're going to do is take this product and do that and move all the k's to the right and all the n's to the left, or n primes if you like. What we'll end up with on the left is a product of a bunch of things in n. I don't know what those things are. Probably they're not n1 through n sub r, but they're in n, right? Maybe they got primes on them. I don't know. But we can get a product of elements of capital N on the left. Take that product represented by the single letter lowercase n. And on the right, we've got a product of k's. Now, k's stay in the same order. The n's stay in the same order as well, though they pick up primes if you like. But on the right-hand side, we'll have k1, k2 to k sub r. On the left-hand side, we've got, thinking out loud here, something like n1 prime, n2 prime, up through n sub r prime. I think that kind of violates, my conversation violates the location of the prime here, but the idea is you've got a product of elements of n over here. I'm not sure what those elements of n are, but anyhow, you multiply them all together, you get something else in n, denote it with an n. Ooh, and here we've got a product of elements of k. You got yourself an element of n, and in parentheses, you got yourself an element of k. And that's what we're looking for, element of n, element of k. So any product of this form can be written, in this form, and this thing here is an element of nk. We chose x, an arbitrary element of the join. Observe we can write x like this. X is also of this form. X is in nk. So we took an element of the join and showed it's in nk, arbitrary element. We've shown the join is a subset of nk. First observation got us nk as a subset of the join. Down here, we've got the join as a subset of nk. So we get the equality, nk equals the join. You know, you could do all that stuff again, considering kn instead of nk. You'd have to swap the orders on all these. You'd put together a similar argument about moving things to the left and things to the right. The things that were moved to the right before would be moved to the left now. You get the k's on the left and the n's on the right. But the same argument will go to show that kn also equals this. So we've drawn the conclusion that these three sets are equal. Yeah, I guess that's the claim. But we got more than that out of this. We've got, remember, that's a group. Well, if that's a group, these two things must be groups as well. And they're equal to each other. Not that it's a commutative group. We've got commutativity of an, I can't even talk about the commutativity of the elements. There's something about commutativity. Actually, I think the next part of the theorem gives us precisely commutativity of some elements. But I do draw the conclusion that nk equals kn, and that's not something we had in the past. Maybe bigger than that, both of these are groups, and I know that's something we didn't have in the past. The big assumption that's given us that is the normality of subgroup capital N. So N is a normal subgroup. That's the big hypothesis that produces this. Lastly, we assume K was a normal subgroup of G. So we got two normal subgroups of G. K is a normal subgroup hypothesized here. N is a normal subgroup was hypothesized up top. So two normal subgroups that intersect only at the identity. Then element-wise, NK equals KN. Saying these two sets are equal is not saying NK equals KN. Saying every NK is of the form something in K times something in N, but I don't know how these things turn around in general. But in this case, when both are normal, we get commutativity of this sort. That's, let's see, that's, I can't go back up here and say we necessarily get a commutative group under these conditions up here. I'm commuting some of the things. I don't have a complete commutativity result. I might be able to extract one if I put enough hypotheses on it. But the claim is we get this kind of commutativity. for these elements. And again, all this is happening in big group G. Big group G's got a lot of stuff in it, maybe. Here we're getting some kind of commutativity. And this is elements, finally. So K is a normal subgroup of G. All right. Choose K, lowercase k, an element of K, and lowercase n, an element of n. NK n inverse is in K. Yeah, we've got K is a normal subgroup of G. So if I took any element of G, we'd get element of G, call it A. We get A, capital K. A inverse is a subset of K. This is that statement written in terms of elements and n's instead of a's. Elements of K and n instead of A. But this is the same form, A, K, A inverse that we've had before. So first theorem tells us that we'll get this as an element of K, comes from the normality hypothesis. It's one of the set inclusion things rewritten in terms of elements. Let's see, K inverse is an n. So claim here is, since n is a normal subgroup of G, we'll take an element of n, multiply it on the left and the right by an element of G, and its inverse, same argument. So we get this to be an element of n. This is that A inverse is a subset of n part of the first theorem. So same idea here, again, using normality. So we must be on the right track because we've used the hypotheses, normality of K and G and normality of N and G. So we're trying to show this commutativity here. There's the conclusion down below. So if we'll look at NK, N inverse times K inverse, claim is that's in K. Follow the clues. See, NK, N inverse, there it is in K, and K is in K, so K inverse is in K. In parentheses, element of K, K inverse is an element of K. Of course, the product is an element of K. Also, NK, N inverse, K inverse, same thing, can be written, associativity, move the parentheses over one, same order, just group the last three instead of the first three. This involves K, N inverse, K inverse. K, N inverse, K inverse, that's an element of N. And N over here is an element of N. It's given there. Element of N times element of N is an element of N. All right. Why don't we look at this? We've shown this thing is in K, and we've shown this thing, same thing, is also in N. So this thing, NK, N inverse, K inverse, NK, N inverse, K inverse, is in both N and K. It's in the intersection. But the only place those intersect is at the identity. Well, then it must be the case that this element equals the identity, effectively cross-multiply, multiply on the right by K, N, and you'll produce the equation NK equals KN. That's the commutativity. We chose arbitrary K's and N's in the first line. We've drawn this conclusion. Big time using the normality hypotheses. And there's your commutativity with respect to those elements. Back to the notes. Okay, so there's some properties of normal subgroups given to us in terms of the definition. What's your interest in normal subgroups? We can make quotient groups using normal subgroups. And that's the next result. So the following result is a big one. It says that if N is a normal subgroup of group G, then we can form a group out of the cosets of N by defining a binary operation on the cosets using representatives of the cosets. Sounds exotic. We encountered something like this earlier. Also, when you do arithmetic, mod n, z sub n, that additive group, you're doing addition of equivalence classes by representatives. The reduction mod n, when you do the addition, is effectively doing the addition using representatives. This idea of making quotient groups, or if you like, factor groups, using normal subgroups. This is a big result. I mean, you spend a good deal of time doing this in senior level algebra. This is a backbone of modern algebra, I've said. Okay, theorem 1.5.4 says, if n is a normal subgroup of a group G, and, let's read this, G mod n, we've done this before, is a set of all left cosets, say, also holds for right cosets, of n and G, then G mod n is a group of order, index of n and G, under the binary operation given here. Left cosets, well, I just needed some symbols to write. If we've got a normal subgroup, which we've hypothesized, left and right cosets are the same. So this could also be written in times A. Binary operation n times B equals n times AB. Right? I just move the letters to the right instead of the left when multiplied on those sets. Right. Normal subgroups, left and right cosets are the same. So this could be written in terms of right cosets instead of left cosets. So there's no particular claim there. Now, we had shown earlier that if we had a congruence relation, then the congruence classes formed a group. And you define the binary operation using representatives. That's exactly what we're doing here. Only, do we have a congruence relation here? We have congruence mod n. That's an equivalence relation. Actually, all we need to do, well, almost all we need to do is show that equivalence relation is a congruence relation, and that's how the proof will go. Let's peek ahead to the definition. If n is a normal subgroup of G, then this group we just discussed, G mod n, is called a quotient group of G by n. I'll probably let this term sort of fade into the background. It's not mentioned at all, I don't think, in Hungerford, and we'll stick with the term quotient groups. So if n is a normal subgroup, G mod n, that's a quotient group. If you don't use normal subgroups and you try to make a group out of the cosets, it doesn't work. So I think we'll touch on that in passing at least. But the normal subgroups allow you to show this is a well-defined binary operation. So let's look at the proof of that one. Okay. Much of the work's already done by theorem 1.1.5. That's the one that said if you have a congruence relation, you can make a group out of the equivalence classes. We've got an equivalence relation. What? Left equivalence or right or congruence, I guess left congruence or right congruence. Those coincide when we have a normal subgroup. So I'll just talk about congruence here and we'll drop the left or right stuff. We do that because we have a normal subgroup. But we know we have an equivalence relation, congruence mod n. The question is it a congruence relation? It is, and that's what we need to show. So theorem 1.1.5, if you have a congruence relation, then you can use equivalence classes. Here the equivalence classes under congruence mod n are the cosets. All right, so for G, an element of big group G, coset, Gn, say left coset, right coset, doesn't matter, they're equal. We have a normal subgroup n. This coset is the equivalence class of G under the equivalence relation of congruence modulo n. And I don't have to talk left or right, normal subgroup, they're the same. Theorem 1.4.2, part 2, I guess, gave us that. So the cosets are equivalence classes, and we're trying to make a group out of the cosets. Well, they're equivalence classes. This will work, says theorem 1.1.5, if our congruence modulo n really is a congruence relation. Remember what that said? We had a congruence relation if when A1 is related to A2 and B1 is related to B2, then we need A1 times B1 related to A2 times B2. Or A1 congruent to A2, B1 congruent to B2 implies the product. A1, B1 is congruent to the product A2, B2. We could talk equivalence relations on sets without any of this congruence relation stuff. Yeah, a set's just a bunch of elements. A group is a set of elements, and there's a binary operation on it. So equivalence relations, I don't need to talk about binary relations, and congruence relation on a set doesn't even make sense. It requires the multiplication in the group as part of the definition. Well, we're set. We've got an equivalence relation. We've got equivalence mod n. Left, right, doesn't matter. We got a normal subgroup. So suppose A1 is congruent to A2 mod n, B1 is congruent to B2 mod n. That means, say in terms of right congruence, that means A1, A2 inverse is an element of n. Let's call it n sub a. And B1 is congruent to B2, right congruent, means B1, B2 inverse is an element of n. Let's call it n sub b. We want to show that this occurs, that is, the element on the left times the inverse of the element on the right is in subgroup capital N. So we're trying to get this to be an element of capital N. And that's what we had up here. That's what the relation means is in our setting. This thing times that thing inverse is in capital N. This thing times that thing inverse is in capital N. This thing times that thing inverse is in capital N. This thing times that thing inverse we need to show is in capital N. So let's do some algebra. First, the inverse of the product is the product of the inverses in the other order. There's a B1, B2 inverse. We were just talking about that. We denoted it as n sub b. So let's replace B1, B2 inverse with n sub b. All right. N is a normal subgroup of G, hypotheses. First thing out of our mouth in Theorem 1.5.4, N's a normal subgroup. So, in particular, the left coset, A1 times N equals the right coset, N times A1, part 3, the first thing we encountered. So, here we've got A1 N sub B. So A1 N sub B can be written as something in N times A1. Take N sub B from set N, which we know it is. N sub B is an element of capital N. And that has to be also an element of this because they're the same set, similar trick to what we had before. So I get some element of capital N times A1 to give that same element. Some N. So I don't know what lowercase n is specifically, but I know where it is. It's in capital N. So we get A1 N sub B equals N A1. Kind of allows us in some sense to, I want to use the word commute. We got the A1 on the right. Yeah, the behavior of equivalence of left and right cosets lets us do that. Some other things happened. I lost N sub B, it got replaced with something else. But I know where that something else is. So we get this relationship. Now, we left off with A1, B1 times A2, B2 inverse. We left off here. A1 N sub B, A2 inverse, same thing. All right, we just showed the A1 N sub B can be written as N A1. So we'll substitute these first two things together for N A1. All right. A1, A2 inverse, let's associate those with each other. A1, A2 inverse, we were talking about that earlier, that's N sub A, which lives in N. So we've got N times N sub A. N itself is from capital N. N sub A up here was from capital N. So that product is in capital N. Product of two elements of N are again in N, it's a subgroup. And that's what we were trying to show. We were trying to show this times that inverse is an element of capital N. That means this, A1, B1, is right congruent, that's what we've shown, to this, A2, B2. This and this are right congruent or left congruent because of the normal subgroup thing, mod n. And we've shown that this congruence is a congruence relation. If we had A1 congruent to A2 and B1 congruent to B2, then the product A1, B1 is congruent to the product A2, B2, modulo n. All right, so we got a congruence relation. Awesome. Theorem 1.1.5 says, hey, you got a congruence relation. You can make a group out of these. Well, I guess at first it says semigroup. So we get a semigroup. There is an identity. Here's how we're defining the binary operation in terms of representatives. The identity would be the left coset identity times n, which is just n itself. This is kind of a big deal. In the quotient group, G mod n, where n's a normal subgroup, the identity element is capital N itself. That's the identity in the quotient group. So we've got a semigroup with an identity. It's got a monoid. And we've got inverses. What do you think the inverse of left coset AN is? It would be A inverse N. Because we have inverses in group G, then we have inverses in these quotient groups, in these equivalence classes. If I take AN times A inverse N, we'll get AA inverse N. That's the identity, and that reduces to N itself, and N itself is the identity in this group. So we have an identity, we have inverses, each element has an inverse, you got yourself a group. So these cosets of a normal subgroup form a group themselves, and there's the binary operation. How do you multiply cosets together? You take a representative of this coset, a representative of that coset, and make that a representative of the product. There's a brand new binary operation being introduced between these two cosets. This is the binary operation is given by this. We didn't put asterisks all over the place, but there's an understood binary operation right there. That's a new binary operation. It's the one in the quotient group. There's a binary operation here between the A and the B, right? Yeah, that's just a regular old binary operation in group G. That's just elements of group G. Yeah, this is just elements of a group, but the group has as its elements cosets. So the elements are cosets, and this is how the binary operation on two cosets is defined. Take an element of this, take an element of that, multiply them together in the group G, and then make that, use that to form a left coset. And similarly for right cosets, doesn't really matter now, does it? We got a normal subgroup, so left and right cosets coincide. Okay. This is a fairly lengthy section. We said such a thing is called a quotient group. We want to link this in together with homomorphisms now. Let's go ahead and do some of that. Theorem 1.5.4 said if we have a normal subgroup, then we can make a quotient group. Fraley actually gives a little bit cleaner if and only if kind of result. Fraley says in his theorem 14.4, let H be a subgroup of group G, then the left coset multiplication is well defined by this if and only if H is a normal subgroup of G. We've shown if we have a normal subgroup, then this works. Fraley goes beyond that and says if you don't have a normal subgroup, this doesn't work. This isn't a well-defined binary operation. If it ain't well-defined, then it's useless. So we've shown, strictly speaking, if we have normal subgroups, then we can make quotient groups. Fraley's gone a little bit further than that and said if you don't have a normal subgroup, then you can't make quotient groups. So the normality is a necessary condition for making subgroups. Informally, when I look at a quotient group, I've taken a big group and I've broken it into little pieces. Maybe I can study the properties of the big group by studying the properties of the little pieces. That's a common explanation for motivation for looking at quotient groups. your most tangible example, and finally, really a definition of the integers mod m in an algebraic way. If we look at the integers mod m, then we need first a subgroup. So let's take the subgroup generated by m, any integer. Remember, we're dealing with addition here. If I take m equals to 0, I get the trivial subgroup. If I take m equals 1, I get all the integers. So I might want to take something a little more interesting than 0 or 1 for m. But we'll take a subgroup of the integers. You know what it is. It's all integer multiples of some m, where m is the smallest positive element of that subgroup. Cosets are of the form k plus m. A subgroup of the integers is going to be normal. Yeah, because the integers are a billion. We got a billion groups, and all the subgroups are normal subgroups. So maybe it's not interesting, but it ain't a bad place to look for examples. So here's what we get for a subgroup. You know what the cosets look like. We've got all the equipment we need then to make a quotient group. We could define this quotient group. Integers mod subgroup generated by m. In fact, that gives the integers mod m as a subgroup, as a quotient group, the elements of which are equivalence classes. And whenever we looked at the integers mod m, I was very careful to put little bars over 0, 0 bar, 1 bar, and so forth, up through m minus 1 bar, because those represented not integers, they represented equivalence classes of integers. And now that discussion fits in perfectly here. So it takes until this point where we can talk quotient groups. But what the integers mod m is really is the integers, a quotient group of the integers and this particular subgroup. How many cosets are there of this in the integers? There's m of them. Yeah, that's the m elements, equivalence classes. Cosets, equivalence classes, same thing. With normal subgroups, everything works fine. That is the m elements of the integers mod m, 0 bar, 1 bar, and so forth. Okay, shifting gears a little bit and talking about homomorphisms. Fraley introduces quotient groups by first considering the kernel of a homomorphism. Takes a kernel of a homomorphism and uses that to make quotient groups, factor groups as he calls it, and only later talks about normal subgroups. We're doing it in a different order. So instead of starting with a homomorphism and talking about normal subgroups later, we started with normal subgroups, and we'll talk about homomorphisms later and kernels of homomorphisms later. So we're kind of going in opposite directions, but we'll all end up in the same place. So to link those ideas together, let's look at Theorem 1.5.5 says, if F, mapping group G into group H, is a homomorphism of groups, then the kernel of that homomorphism is a normal subgroup of G. Kernels of homomorphisms are normal subgroups. Okay, so then we can make quotient groups out of kernels of homomorphisms. Conversely, if N is a normal subgroup of G, then they're defining a map, pi, projection, that maps G to the quotient group, G mod N. N's a normal subgroup, so it makes sense to talk about the quotient group now. This pi mapping takes element A of G and maps it to coset AN, the coset containing element A. This is an epimorphism, an onto homomorphism with kernel N is the claim here. I bet you it ain't necessarily one-to-one. This mapping pi is called the canonical epimorphism, canonical homomorphism. It was called in Fraley, if you had that as background. We haven't seen the last of this pi projection mapping. The canonical epimorphism will arise a number of times. Okay, so we've made two claims, kind of in different directions. Let's go through the proof of that. It's only one slide. It's pretty crowded, but claim is. Oh, sorry, that's a previous one. Here we go. This one just can't be one slide. Two claims. All right. Let's see. If F is a homomorphism, then the kernel is a normal subgroup. All right. So take F as a homomorphism and let X be in the kernel of F. Let A be an element of G, arbitrary element of the big group G. I can't say G is an umbrella group. We're working in two settings here. We've got group G on the left and group H on the right. And somewhere along the lines, a quotient group is going to pop up. So things aren't all happening inside group G anymore. It's gotten more interesting. But take X to be in the kernel of this homomorphism. So this would be something that's mapped to the identity of H under F. If we consider F of AX, A inverse, F being a homomorphism, preserves binary operations. This is F of A, F of X, F of A inverse. We said X is in the kernel of F. The kernel of a homomorphism is the stuff in G mapped to the identity of H. Definition of kernel of a homomorphism. So if X is in the kernel of F, then F of X is the identity of H. It's denoted E sub H here. Inside AX, A inverse, that involves a binary operation in group G. F has taken us over to group H. So the binary operations between these things is the binary operation in group H. F of X is the identity in H because X is in the kernel of F. We pick up an identity. We can eliminate it from the discussion. Homomorphism, F of this times F of that is F of this times that, right? Again, here's a binary operation in H. Inside here is a binary operation in G just because of where we're mapping from and to. AA inverse, that's the identity in G. And you know, a homomorphism always maps an identity to an identity. It was an early exercise, I think. So what we've shown is if we take an arbitrary element of the kernel and an arbitrary element in big group G, it's a big group on the left, then AX, A inverse under homomorphism F is mapped to the identity of H. In other words, AX, A inverse is in the kernel of F. We've done that for arbitrary element of the kernel. So what we've shown then, X is an arbitrary element of the kernel, is swapped from element notation to set notation. We'll take the kernel of F, multiply on the left by A and the right by A inverse, A an arbitrary element, blah, blah, blah. We get a subset of the kernel of F. So we've taken kernel of F, multiplied on the left and the right by A and A inverse, arbitrary element of A, and we've got a subgroup of that kernel. In your mind, replace kernel with capital N. We've got A capital N, A inverse is a subset of capital N. Well, that was one of those things in theorem 1.5.1. It was a fourth part. And so that was a condition that gives you that this thing here, capital N, kernel of F, is a normal subgroup of the big group. The big group we're talking about on the left is group G. And we took the A's to be from group G. So that gives away what it's a normal subgroup of. So we get the kernel of F as a normal subgroup of G, and that was the first claim. Second claim, maybe we do get this one done in one slide, excellent. Second claim, if N is a normal subgroup of G, then this particular mapping, as given, is an epimorphism onto homomorphism. So two claims, onto surjective and homomorphism. Oh, and with kernel N, three claims. So suppose N is a normal subgroup. Pi mapping group G into the quotient group given by what they told us to use, pi of a equals an. So we take an element of g into pi, and we get out an element of the quotient group. Elements of the quotient group are cosets in g of n. So we get out left cosets, say, doesn't matter because we got a normal subgroup, say the left coset an. So take element an to pi and get out of pi a times capital N, symbolically, this. All right, this claim here is it's clearly on to, well, you get all the cosets out. You tell me which coset you want to get out. You want to get k times n out? Just put k in, right? So the input on pi ranges over all elements of g, so we'll get all cosets of n out, all left cosets if you like. So we do have the onto property, the surjective property. About the homomorphism property, it's pretty easy given the way we've defined coset multiplication in the quotient group. Pi of AB, okay, by definition, when I take something into pi, I take that something and multiply subgroup n on the left by that something. We're taking AB in, we'll get out AB times n. So we've got out a left coset. Hey, that's an element of the quotient group. And you know what? AB times n equals an times bn. Over here, that's how we define coset multiplication. Previous theorem said this is the binary operation in the quotient group. Use this, you actually get a group, if n is a normal subgroup of big group G. So we get from here to here, this equal sign is justified by the definition of coset multiplication. What is A times n? Well, in terms of pi, remember we're trying to show homomorphism, that's pi of A. It says so right there. So Bn is pi of B. That's how the mapping works. So this is pi of A. This is pi of B. There's the equality there. And we've shown pi of AB equals pi of A, pi of B. That's a homomorphism. So we've got the onto property. We've got the homomorphism property. So we've got an epimorphism, an onto homomorphism, a surjective homomorphism. So that establishes the homomorphism claim. The kernel is in. Kernel of pi would be the stuff in G such that, call it A, such that pi of A equals the identity, remember pi maps from G to the quotient group, the identity in the quotient group. Just said the identity in the quotient group G mod n is coset n itself. So pi of A being in the kernel must map, or pi, A being in the kernel of pi of A must be the identity in the quotient group, must be just n or the identity times n if you like. So we get the identity out in the quotient group, and the identity in the quotient group is n itself. So we're looking at all A such that pi of A equals n. That'd be all A in G such that pi of A was an. So replace the pi of A with the left coset an. We need that to equal n, just substitution of this, drop that. And we get an equals n. When is it that left coset an equals n? And we chatted about this. I don't know how formally we stated it, but that's only going to happen when A itself is an element of n. Think of it, if I take an element of a group, what's it do to that group? It permutes the elements around. Think about the line in a Cayley table. And what you're doing is along the top, you've got all the elements of the group. You've chosen an element on the left, like an A, and now you've done the product. What do you get in a row? You get all the elements in the group in some order. So it permutes the elements around. So the only way we're going to get an to equal n is when A itself is in n. And we just showed that the kernel of pi then is all A and G that are in N. In other words, the kernel of pi is in itself, and that was a claim. Okay, so that gets us introduced to homomorphisms producing normal subgroups, and also the canonical homomorphism. Back to the notes. The next result, let's look at, maybe look at a picture for this one. This is similar to one of Fraley's results, the fundamental homomorphism theorem. A lot of stuff will follow from this. It says if F mapping G into H is a homomorphism and N is a normal subgroup of G contained in the kernel of F, then there's a unique homomorphism F bar mapping the quotient group G mod N into H such that F bar of AN, this is an element indeed of the quotient group, it's a left coset, F bar of AN is the same as F of A for all A and G. In addition, the image of F and the image of F bar are the same. The kernel of F bar is the kernel of F mod N. It says up here, in particular, N's a normal subgroup that contains the kernel of F. So the homomorphism came first, then normal subgroup. The normal subgroup was required to contain the kernel of the given homomorphism. And then we claimed the existence of a unique homomorphism, this one mapping a quotient group into H, F itself mapping G into H. And we got a relationship between that unique homomorphism mapping the quotient group to H with homomorphism F mapping group G into H in terms of values and in terms of images and a relationship between their kernels. Let's go through the proof first. Okay, next. All right. First, we need to introduce this F bar thing. This is not terribly lengthy. I think it stretches over 3 slides, but there's not a pile of information on each of them. First, introduce the F bar mapping. We want this. If B is an element of left coset AN, then B equals A times N for some N. That's what it means to be in a left coset. We were given homomorphism F, so we can apply homomorphism F to this element B, but it came from a particular place. We want to talk about how cosets are mapped here shortly, but in terms of F, that's mapping of elements themselves. F of B, that is F of AN, B equals AN. If it's a homomorphism, that's F of A times F of N. All right. N comes from subgroup capital N. Capital N is a normal subgroup contained in the kernel. Hope I read that correctly before. Capital N is contained in the kernel, so this element lowercase n is contained in the kernel. Capital N is contained in the kernel, so is element n then. So F of N, being in the kernel of F, must get mapped to the identity of the group on the right, group H, call it E sub H. So we just get F of A back out. So we've got, when B is chosen from coset AN, that F of B equals F of A. So regardless of which element from this left coset we choose, this coset AN, we get F of A back out, regardless of which representative from this coset that's chosen. Anything chosen from this coset into homomorphism F produces the same thing, in other words. All right, so remember we're trying to define a mapping on cosets, so we're trying to get to well-defined. So B is any representative of the coset, the left coset AN. So if we define F bar mapping cosets, mapping the quotient group, the elements of which are cosets of N, mapping cosets to H, define F bar as AN equals F of A. This is well defined. So a coset AN might also be represented by Bn. We could have AN equals Bn. If A and B are congruent, mod n, that could happen. Remember, it's a whole set of elements. We're picking one element in that set, this representative A, in our definition of the F bar. We're defining it as F of A. What this says is no matter what you had chosen from that left coset AN, you would have got the same thing out. That's what this argument is. So we're good in defining F bar of a left coset in terms of a representative. All representatives, such as B, produce the same thing. F of B equals F of A. So the right-hand side will be the same, even if I choose something different from this coset and plug that into F itself. F itself sounds like it's big time, not one-to-one. Homomorphism, but not one-to-one, unless these cosets have cardinality 1. So this does define a well-defined F bar. So we're to this stage. So we've got the F bar defined. There's a uniqueness claim and a homomorphism claim. Okay, let's establish the homomorphism stuff first. Let's take F bar of left coset AN times left coset BN. How do you multiply cosets together? Using representatives. So we get AB times N using the multiplication inside the quotient group, G mod N. So that produces this. What does F bar do to that? It simply takes that representative and we get F of the representative. F of this thing times N equals F of this thing. Okay. Sorry, F bar here. So F bar of whatever times N equals F of whatever. We drop the bar, drop the N. Drop the bar, drop the N, it produces this. That's the pattern. Okay, now we're dealing with F. F's a homomorphism. F is a homomorphism by hypothesis. So we're kind of back to the original setting. So F of AB is F of A, F of B, but we're trying to show F bar is a homomorphism. What is F of A? F bar of AN. What's F of B? It'd be F bar of BN. That's how F bar is defined. And we've shown then that F bar of AN times BN is F bar of AN times F bar of BN. Don't make me go on and on about where the binary operations are. They're in different places. Sometimes they're cosets and they're in the quotient group. This is out there. I don't know, where does F bar take us? H. This must be the binary operation in H. So I will go on about it. So we do have the property of homomorphism satisfied. So that takes care of the homomorphism claim. So this is a homomorphism. Made a claim about the image of F and the image of F bar are the same. Does that make any sense at all? Well, first off, the image of F is a subset of H, and the image of F bar is also a subset of H. So yeah, the stuff in the images of these, at least they live in the same place. They both live in subgroup, or sorry, in group H. So we at least got that going for us. So we want to show the images are the same. The definition of F bar as F bar of AN equals F of A. Image is the range of a function. So as A ranges over all the elements of G, AN ranges over all of the cosets, and we've set these things equal to each other. So everything that can come out of this is exactly what can come out of this. So the images of those two mappings are the same. Let's see, that takes care of the image claim. I'm going to look at the kernel of F bar. Let's look at this part next. I think this comes next. If AN is a left coset in the kernel of F bar, remember, maps the quotient group to H. So if we've got something in the kernel of F bar, that means that occurs if and only if F bar of that thing equals the identity. So F bar of this element of the kernel must give us the identity. I didn't document this terribly well. Identity where? What comes out of F bar? Elements of H. So arguably I could put a subscript of H on this. All the homomorphisms are going to map into H. So we'll only have a conversation with kernels about one of the identities, but it might be prettier if I put a H on there. It's the identity in group H. And we have this equality if and only if f of A equals the identity, because remember, f of A and f bar of A is in, those are the same things, how the f bar was defined. So it's substituting this with that. So we get f of A equals the identity. Well, then A is mapped to the identity under F. So that means little a is in the kernel of F. So we got A in a kernel of F bar, if and only if, stringing together those double implications, A is in the kernel of F. So kernel of F bar is all A in, such that A is in the kernel of F. That's established here. A in, such that A is in the kernel of F. Why, that is the kernel of F mod n. Kernel of F being all these A's. So what we've done is taken the coset of n in the kernel of F. That would be all left cosets of the n inside this bigger group. Remember, n was a normal subgroup contained in the kernel of F. So subgroup contained in the kernel, let the A's range over the larger group, and that produces the collection of cosets. So the kernel of F bar really is the kernel of F mod n. That was claimed, so that takes care of, let's see, the kernel claim. I still have the uniqueness claim up here. We've defined F bar entirely in terms of F, and the F bar was defined like this. So given that F bar is determined by the given homomorphism F, there's no other alternatives on the F bar. It's uniquely defined because it's defined totally by this requirement that it equal the given homomorphism F. So there's your uniqueness. We're left with F bar as an isomorphism if and only if F is an epimorphism and n equals the kernel of F. Okay, so we got that last claim to deal with, the isomorphism claim. Let's see, F bar is an onto homomorphism. We established the homomorphism property earlier. Unique homomorphism, we probably established the homomorphism property of F bar earlier. We made an observation about onto-ness as well. So what we're worried about is the one-to-oneness, the injectivity. Theorem 1.2.3 says F bar is one-to-one, a homomorphism is one-to-one, is injective, if and only if its kernel consists only of the identity. So we're looking at F bar. The kernel of F bar would have to be the identity in this quotient group. The identity in a quotient group is the denominator itself. Let me call that denominator in the quotient group G mod n, of which the elements are cosets. The identity in that group is n itself. Kernel of F mod n, the identity is n itself. So we have the kernel of F is one-to-one if and only if the kernel of F mod n equals n itself. So we need for the one-to-oneness, we need this to equal n itself. So we need the kernel of F mod n to equal n. And in a quotient group, mod n, the only time you get n itself out is when the kernel of F is n. You're only getting one coset out. Well, then that happens when we have n mod n, say. So it must be that the kernel of F equals n itself, and that was the claim here. That gives us a one-to-oneness, and that occurs, the if and only if claim supported right here. N equals the kernel of F. So not terribly tangible stuff, not terribly glamorous, but it is allowing us to talk homomorphisms and connections with these normal subgroups. So let's see, I want to make one last, let's make one last observation. What we've done here, I claim, so let me go up and get the canonical epimorphism. This F bar, the way it was defined, we took a left coset here. This AN thing, actually, that reminds me of the canonical morphism, canonical epimorphism. Pi of A equals AN. Well, this F bar takes AN in. Well, we could view that AN down there as a pi of A. We could have F bar of pi of A, right? This is a composition. And we'd have F bar composed with pi, the canonical epimorphism, equal to F of A. We'd have a composition equal to F. Hungerford talks about commutative diagrams. This is a big deal if we were to do a lot of ring theory. It's rather deep in the book. In a one-year course, we probably wouldn't get that much ring theory accomplished, only at the expense of something else. But commutative diagrams, just to give a quick idea of what that is, it's something of this form. We had G mapped to H under F. We had G mapped to the quotient group under the canonical epimorphism pi. And what we've shown up here in the statement, F of A equals F bar of pi of A, if you like, is that we can map G straight over to H with F. That was the F of A stuff. Or we could take G, use the canonical epimorphism, map it to a quotient group, and then use F bar to map that quotient group over to H. F did the same thing as pi composed with F bar did. Pi takes A and produces AN, and then F bar takes AN, left coset, and produces F of A. So they didn't write this explicitly as a composition with a canonical epimorphism, but it is. Just take the AN down there and replace it with a pi of A, and poof, there's your composition. First there's pi, and then there's F bar. And that does the same thing that F does. Or in the verbiage of a commutative diagram, we can either go along here or go follow this collection of arrows. These arrows, these arcs in the diagram, if you like graph theory, and we get the same result out. So that's what they mean by commutative diagram. It's explained in a bit more detail. This is being an elementary example, but this is an example of a commutative diagram. Go this way or go that way. You end up in the same place with the same values. Start with A here. We produce the same thing with F as we do by first pi-ing A to get left coset AN, and then F barring A to get F of A out. That should be enough of that for a while. What we'll do next is get into the isomorphism theorems. I can't promise it gets a whole lot more tangible. So in my opinion, this is where algebra starts to get really good and abstract when you encounter this quotient group stuff. But more of that soon. I'm going to take a little break and we'll come back and finish section 1.5 here a little bit later. Have a nice day.